Hello and welcome to Lecture 33 of our course From Data to Decisions. I'm Chris Mack, your instructor for this class, and today we'll look at total regression in R. I'm going to use two different techniques. One's a bit manual. I'm going to use an effective variance technique where I'm just going to use the weighted regression functions of LM, the linear modeling capability of R. And then I'm going to also look at Deming regression. So I have two different scripts, both of which are on the website, and you can download. The first one is called total regression _ effective variance, and it's where I'll implement a very simple effective variance technique for doing a total regression. First, I've got this routine that I've written called the 4-graph summary. It simply takes the 4-graph technique of looking at regression results, and I put it into a function. So if you're interested in seeing how functions work, you can take a look at that code. I have to execute it one time, and then it's available for me to call anytime I need it in the rest of the routine. All right, so what I'm going to do is kind of create some fake data. I'll assume that my ideal model, my ideal response goes as x squared, so I'll have a sequence of x values that go from 10 to 40 in steps of 0.5, and then I'll say y ideal is equal to x squared. Then I'm going to add some error. I'm going to use, as I've done before, the rnorm function, which creates random numbers from a normal distribution. That's going to create n of them of data. I will use y ideal as the mean and SD as the standard deviation. And what I'm going to do here is create a standard deviation that has heteroscedasticity. In fact, it will be the exact kind of heteroscedasticity you get when you have variance in the x variable and you have a nonlinear function. So I am in fact creating the perfect kind of error scenario for which nonlinear regression is ideally suited. Total regression is ideally suited. All right, so let me generate some data. There it is. Our normal way of modeling would be to use LM, linear model, so just a standard linear regression. So let me go ahead and perform that regression, get a summary of the model and our 4-graph summary. Control R. Here in the console, I see the results of my regression, in particular intercept and slope, their standard errors, residual squared errors, etc., etc. Here's the 4-graph summary. So you can see what the data looks like, the model in red. The residuals has a little bit of this megaphone behavior where the smallest spread of residuals is at the low values of the predicted variable, and then it spreads wider. QQ plot and the Williams graph, all showing exactly the kind of results we might expect under these circumstances. Now I'm going to use the effective variance approach. To do this, I have to have some a priori knowledge of what I think is the sources of variation in x and y. So let's assume that ahead of time I have learned that each x value has a standard deviation of 1.5. Remember, my x values went from 10 to 40, so 1.5 is a reasonable amount of uncertainty in each of those values. Let's also assume that each y value has an uncertainty or standard deviation of 10. Now, I picked those numbers because it matches exactly the simulated data that I created. So again, it's a little bit of an artificial exercise because we generally don't know what is the right thing to do, but let's assume that we had good knowledge of our measurement errors and why we had uncertainty in x and y. To use the effective variance approach, we have to use the equations we had in the text, in the lectures rather, and we have to begin by taking the derivative of the model. So a model is simply x squared, or a slope times x squared, or a coefficient b1 times x squared. So I take the derivative of that, I'll end up with a slope of 2bx1. Right, so that's what 2bx rather. So that's what this equation says. B1 we'll get from the model coefficients of our ordinary least squares regression. That'll be the way we estimate what this coefficient of x squared is. Then I calculate the slope and the standard deviation, because I assume that standard deviation is 1.5 for the x, and the standard deviation in x as it's reflected onto y is the slope times 1.5. I'm also assuming the standard deviation of y is 10, and therefore the effective variance is sdy squared plus sdx squared. Sdx is the standard deviation in x as it's reflected up onto the y-axis. We're calculating the effective variance in order to create a weight and do a weighted regression. So the weight will be 1 over the effective variance. All right, so let me execute all that. And then we will have a model, which is simply the linear model, LM, using the weighted function, weights equal W. So when I run that, I get a new set of graphs. Notice now, because I've weighted things properly, my residuals are more evenly distributed, all from low to high values. Well, this is one iteration. Now that we've fit it a second time using a weighted regression, we have a new estimate for the model parameter B1 that multiplies x squared. So I could go ahead and do a third iteration. It's the third iteration. It's the exact same thing as the previous iteration, but I use for B1, the slope, the coefficient multiplying x squared, I use now model output of the second iteration, the time I did the weighted regression. All right, so I can just rerun that again. And I get a new model, new results. They don't look very different from the results. Let's compare. I'm going to use this coefficients function. Coefficients of the model tells us all the model parameters of that model. So I've got 3 models. The first one was the ordinary least squared. The second one was our first iteration using the effective variance technique. And the third model was our second iteration using the effective variance. So let me just summarize all those coefficients. All right, so I can see 1, 2, and 3 right in a row. You see my original slope is 1.0105. By the time I did our first iteration using the weighted regression, the effective variance technique, the slope went up a little bit to 1.0, the slope. I keep saying slope. It's the coefficient of x squared. It's the slope if I happen to be plotting x squared on the x-axis. But the coefficient of the parameter x squared went up. It's now 1.0205. Now, if I do a third iteration, notice that it goes up to 1.0205. All right? In fact, it's only very slightly different from the previous iteration. You can also look at the intercepts. It goes from -10 to -17, but then it stays stable. So basically, it only took one iteration to arrive at a converged answer using the effective variance approach. 2 iterations were required just to confirm that we had achieved stability in our estimates. That's how we use the effective variance approach. Interestingly, we could also, if I uncomment this line, we could use our formula to make a better prediction for what x is as well. Let's suppose I did that in the first iteration. I not only used the effective variance to weight the y values, but I used the residuals and the slope and the effective variance to make a better estimate of the x variables. All right? Let's call that x hat. Then I will model y versus x hat squared. and ask how that goes. So let me go ahead and run all of that code. And now here's my 4-plot summary of that. Notice what's happening. That's very strange. Look at how our model seems to be passing weirdly through every single data point. That's because I'm no longer fitting to the x values that I'm plotting. I'm fitting to the x hat values. And in fact, if I went ahead and called this x hat simply x so I could graph it using my 4-graph summary without having to change any code, look what happens. My variation is almost all going away because I'm not only predicting the y values, I'm predicting the x values, and I'm wiggling them so that they fit the model better. And the result is, of course, a much better fit. If I iterated this a few times, all end up lining up on that graph perfectly because I'm using the residuals to make adjustments to the x to get them to fit better. Whether you decide to make modifications to the x or not, the effective variance approach is a pretty simple way to do total regression. Another thing you can do is the Deming regression. Let's start by creating some very simple data. This will just have a constant variance. I'm not going to try to fake it to match any specific heteroscedasticity behavior. I'm just going to assume a constant variance. And I'll create some data. Let me get rid of these old graphs. And I'm going to do two things. I'm going to plot, or I'm going to model y given x. So LM will be y as a function of x. But I'll also model x versus y and look at the summaries. So if I run those two, I'll get two different slopes. The first slope, which is modeling y versus x, I get 0.9482. If I just flip that upside down, switch the axes, I would get 1 over 0.9, just something like 1.2 or something, 1.1. But instead, when I model x given y, I get a slope of 0.705. And if I go 1 over that, I'm going to have a much, much larger value for the slope. If I wanted to calculate the geometric mean of those two slopes, right, these next couple of lines do that for me. So if I run that, I see the geometric mean of those two slopes is 1.16. So this is how we might do a geometric mean calculation. But what I like to do now is look at a Deming calculation. And the Deming calculation will require a new package called the MCR package. This is the method comparison regression package because it's used to compare two different methods of measuring the same thing. Right? That's the main use of a Deming regression or orthogonal regression. And this MCR package, it has a routine called MCReg, which is what we'll be using. It in fact has a number of different methods that you can play around with. We're only going to use the Deming method. So I've already installed the MCR package. You'll have to instantiate the library, and then you can run. Now, this package requires something called the error ratio. The error ratio is defined in this package is exactly 1 over lambda, as I defined lambda in the class. Lambda in the class was variance of the y variable divided by the variance of the x variable when I made single measurements. So here the error ratio is 1 over that. Right? So it's important to keep track of how that's defined in different programs. So I have to define what lambda I want. Let's do a simple experiment first. Let's take lambda and say it's equal to the variance of y divided by the variance of x. what we saw in the last lecture was if lambda is equal to the variance in y divided by the variance of x, then Deming regression should give us the exact same answer as a geometric mean regression. Right? We got the geometric mean slope right here, 1.16. Let's try that. Let me set lambda to be that value. Then I will run this regression, MC-reg, using the Deming method. Okay. Now there's a little print summary. Oops. There's a little print summary function that I will run, and it will print a summary of my regression results. And there's the slope, 1.59223, which is the exact same number we got before from our geometric mean. So worked out just as promised. If we use lambda equal to 1, we would end up with a orthogonal regression. Let's try it with lambda of 2. That'll be our example here. Now with that, we can run a Deming regression and see the results. And here we get a slope of 1.11 approximately. If we compare that all the way to our original y versus x ordinary least squares regression, we had a 1.01 for the slope. Oh no, that's not the right one. Well, heck, let me just go back and run it again so I don't get myself confused. All right, so that's 0.95 we had before. Remember, if we ignore bias in our ordinary least squares, if we ignore x uncertainty in our least squares regression, it always biases the slope to be lower. If we include that, as we did here in the Deming regression, we get a slope that's higher, 1.1 in this case. There's a few functions. str dumps out a string of all the basic output results, but there's a number of functions. For example, there's the get residuals function. If I run that function, it gives me a table of 3 residuals. Find it here. Yes, so the x residual, the y residual, and the optimized residual, the Deming residual. And we talked about that in the last lecture, that there are going to be 3 different residuals that you can get. I also showed in class a analytic equation using the method of moments approach, estimating the standard error of the slope. Here it gives me an estimate of 0.122. Right? And if I compare that to what we got from the Deming regression fit, it's 0.125. So it's only a little bit off from what the package has given us as an answer. And finally, let's do a plot comparing our Deming regression to an ordinary least squares regression. So there's our graph. See that these two are different in the slope, and as we've always said, the ordinary least squares regression is biased to a lower slope, biased towards 0, because we've ignored uncertainty in the x. Well, that's how we do a Deming regression in R. Till the next lecture. See you then.